Thank you, Henry, for introducing and Zhixin for inviting me to give this talk. And can I start? Okay.
Yes, please.
Okay, yeah. So today's topic, it's a guided tour on the map of quantum computing. So I'm supposed to give some basic introduction on quantum computing, and so I will focus on more the basic concepts and the overall big pictures on things. And I would not go into very details about any algorithms or things like that. And let's begin. So I think it's very interesting. I choose this title because I think a couple months ago I came across this map, and this is made by some, I think he's a former PhD from UK and working on quantum systems. And it's very interesting to have this kind of summary. And what I'm going to do is kind of have a tour on this map, maybe not exactly follow his formulation, but there are interesting things I want to cover on this. So yeah, I know it's really quite small. We cannot directly look in that. And please let me move on and tell you my plan. So first, I'm going to talk about basic concepts about what is a qubit, what is a quantum circuit, and how you do quantum measurements. Then I'm going to talk about quantum hardwares, mostly talking about superconducting qubits and ion traps. Just basically talking about their physical realization, but not digging into details. What's more importantly, I'm going to talk about the benchmarks of existing quantum hardwares and make a quick comparison. And talking about whether are they accessible to the public or not, and maybe a simple illustration of scalability. After talking about hardware, I'm going to spend some time, maybe 10 minutes, to talk about what I am used to doing, which is mostly variational quantum algorithms, and some part of the quantum machine learning. I think those are very interesting to me. And I'm not going to talk about those classic quantum algorithms like Schwartz or mostly focus on near term. And then I'm going to talk about, give a picture about quantum stack, because except for algorithm and hardware level, there are going to be many intermediate level, and there are a lot of research opportunities there. And Professor Ding from last week, he already gave us a very great summary and beginning, and I will follow up on that and make few comments on those. And finally, I'm going to talk about resources, about information around. If you're doing a PhD, if you're undergrad, there are many opportunities around, and I will just briefly talk about those. So that's kind of an outline. So the first is to make the story complete, why we care about quantum computing. So the typical story people telling you about is, looking back in the past 50 years, looking at Moore's law. So the number of transistors on microchips on your smartphones, on your computers, double every 2 years. And this has been keep going well in the past 50 years. And on the left, I have a picture of Apple's 5 nano process M1 chip, which contains over 100 billion transistors, which is, still on the right track of Moore's law as you look at so the right graph, it's till 2020, but people realize as the size of the transistor gradually shrinks to a few atom levels, eventually we'll encounter some barrier. The transistors will no longer be a reliable bit due to quantum tunneling. So in very plain language, you can think transistor as a switch can be on and off. If you apply a high enough voltage to that, it can let current through and would be on state or the one state. If the current is, if the voltage applied is very low, it's 0 state. But when the transistor gets really, really small, quantum tunneling is going to happen. Electrons will have certain probabilities just pass through the transistor and ignore how high the voltage you apply on that. And that gives us the first motivation to pursuing some new form of computing hardwares. And the second will be, my physics hero, Richard Feynman. He imagined and proposed a quantum simulator in 1980s, over 40 years ago. So he believes, quantum systems follows quantum mechanics. Classical computers cannot follow that scaling. We really need a quantum, the machine follows quantum mechanics to do the simulation job for us. And I think that's also another motivation. And on the right-hand side, we have Schur and Grover's algorithm proposed in 1994 and 96. And those are considered really making quantum computing not just a toy, a mathematical fun model. And these two algorithms has that's significance in history to make quantum computing moving forwards. So Schur's algorithm, it's for integer factoring. It can factor an integer into two, very large integer into two prime factors, and it provides an exponential speed up. On the other hand, Grover's algorithms is used mostly for unstructured database search, unstructured search, and it offers a quadratic speed up. So it's not as great as Schur's algorithm, but considering the data amount we have today, it's if you just put a billion into the square root, you still get a great amount of reduction. So those two algorithms are really motivating the field moving forwards. So we have been talking about quantum algorithms. And next, I want to discuss what people use as quantum computation models, because if you're familiar with quantum computing, you definitely already know we mostly use quantum circuit models, but there are other things going on. For example, on the right-hand side, we have measurement-based quantum computing. So it has the idea was mostly adopted to some photonic systems. First, you have to generate a highly entangled state for all the qubits. Then you don't do any operation. You just do measurements on that sequence by sequence. And those measurements will function as operations you applied on this quantum systems. And it has the name of one-way computing. Okay, so you just keep doing measurements, keeps going, and quantum information keeps flowing. And people have shown this is equivalent to quantum circuit model. So I just want to bring that for completeness. There are more other models, maybe more suitable for certain physical realization. And this is a typical quantum circuit model you would see. So each line represents a qubit. So here we have 2 qubits, and we apply a quantum gate in certain sequence with the timeline. You first apply what's on the leftmost, and keep going to the right, and eventually, everything inside a box with some symbol, it's a quantum gate. And if you see something connecting multiple qubits, it's a multi-qubit gate. And eventually, at the end, we have to do quantum measurements. to convert this quantum information, convert it back to classical information, which is the only information accessible directly to us. This is the quantum circuit modem people mostly widely used in quantum computing research or quantum computing community. In order to actually run this, you have to compile this into physical level pulses and sending that to a real hardware so that you're done with the computation physically. So this is kind of some process you have to do. And with the quantum circuit model, there are multiple components. I would like to give a more detailed introduction. First, apparently, it's a physical qubit. So, like I said before, classical. Sorry, there's some noise around. Okay, I'm back. Okay, so classical bits, it's more like a switch. You can only be on and off. So we can represent as just 0 and 1. But for a quantum bit, it has a very nice, unique property called superposition. It can be a linear combination of those on and off states. And we can write that as a compact state vector. So this bracket notation is usually used in quantum physics. If you're not familiar with, just treat that as a vector. So this is the single bit case. If you want to go from a single qubit space to a multi-qubit space, what you do is you expand the computational basis from 0 and 1 to 0, 0, 0, 1, 1, 0, and 1, 1 by doing tensor products of the vectors. And that's how you expand going to high dimensional Hilbert space. And some other different nice properties of qubits that unique to them is quantum entanglement. You can apply a two-qubit gate or multi-qubit gate to entangle in certain qubit. So this is a non-classical physical correlation. Once they get entangled, then you do an operation on single qubit, and all the other states will be also affected. That's kind of two very powerful thing you have in quantum computer. So for example, if you have a classical bit, you have a 50 bit, it just, you can be in one of the 2 to the 50 states, but for quantum bit, for quantum system, it can be a superposition of all those states. It can explore much more space compared to classical bits. And I would like to move on to quantum gates. So qubits are kind of the data type you have in this computation. And quantum gates are the operation you actually do, something you do to the data. We can start with the single qubit gate, which is the X gate. It is the NOT gate. You flip the 0 state to 1 state and flip it back from 1 to 0. And when you implement the gate, it simply means you're doing matrix multiplication. And those quantum circuits has to certify certain quantum gates has to certify certain constraints, which is itself times the U dagger. Dagger means you transpose that and doing complex conjugate. And this has to be identity. So physically, that means every circuit you're running, it has an inverse directly. You can just run the circuit backwards from right to left and convert all the parameters inside. You put a minus in front, and that's the inverse you can have. Also, other property of unitary is you don't lose any qubit during the computation. The vector length is still the same, so you don't lose any bits of information because according to physics, if you lose one bit of information, it will introduce KB line 2 energy to the system. So this will heating up and as a source of decoherence to a system, which is not good. That's the single qubit gate. And for 2 qubit gates, people usually work with something called C0. It's the control NOT gate. Depends on the state of first qubit. You will either apply or not apply a NOT gate on the second qubit. So it has the matrix form like this. And I need to introduce the other 3 single qubit rotation gates on the Bloch sphere. So we have been talking about, you know, the qubit can be in superposition on this Bloch sphere. Instead of comparing to the classical bit, it can only in the North Pole and the South Pole. So this operation is XYZ. Correspondingly, you're doing theta, actually 2 theta angle rotation around the XYZ axis. And if you have this 3 single qubit rotation plus the C0 gate, they're a universal gate set, which means you can form an n-qubit arbitrary unitary operation by using this as building blocks. So that's, I think that's one type of quantum 2 qubit gate. It's a native 2 qubit gate. And the other case gonna happen is you can have some idle qubits in the circuit, which means you don't do any operation on that. So it's directly an identity gate. So on the left, this is the circuit diagram, and on the right, this is the matrix you're doing tensor products again to write out the matrix elements of it. And after introducing those building blocks, I would like to take a look at more useful quantum circuit. This is known as hardware efficient ansatz, and we will see more about this. It's called hardware efficient because it has only adjacent C0 gates applied on it. And this is very suitable to superconducting qubits, superconducting quantum chips, because those are also only nearest the neighboring connectivity. You don't have, you don't introduce extra compiling difficulty to when you're transpiling it into the physical paths. Okay, and we see this is a kind of a repeated structure which can be gradually repeat multiple times. And by doing that, you're increasing the expressivity of this circuit. Also, we have many single qubit rotation parameters, theta, in those Ry, Rz. And those parameters could form a vector, a parameterized vector, and offers a degree of freedom to be optimized. We usually call this, you know, circuit with single qubit parameterized rotation as a parameterized quantum circuit, PQC, or denoted as U theta. This will be important and very useful in variational algorithms. Variational algorithm, it's mostly based on this. And the final thing I want to wrap up is it's about quantum measurement. So, so when we do measurement, let's start with a single measurement. If you do a single measurement of once you've done the computation, what you get is a classical bit string with a certain probability. That probability is suppose you're having a superposition state. That probability is the magnitude square of that coefficient in front that the bit string you get. Once you down the measurement, it will collapse the quantum state, leads to something we're not interested. So if you want to recover statistics like this, typically from a quantum computation results, you have to repeat computation plus measurement n times, and n is usually referred as short number. Since we can only repeat this measurement with finite cycles, usually we don't recover the exact distribution. But we can, this is sometimes known as the finite measurement, finite short noise. This can be reduced by, you just do more measurement and make your statistics more accurate. So let's wrap it up. I have introduced a qubit, quantum gate, and measurement. So in order to do a quantum computation, in order to make a quantum computer, these are the 5 criteria people usually refer to. So you have to have a well-characterized qubit, somewhat 2-level quantum system. And the second, you have to initialize it. We usually initialize it into a 0 state to start the computation, but depends on the task. There are more desirable initial states. For example, if you want to doing some classical task, you have to encode the classical data into quantum data first. So you have some initialization process there. And a longer thread basically means you want your coherence time, which is your qubit lifetime, should be much larger than your gate operating time, so that you can have a reasonable amount of circuit depth to run a meaningful task. And you need to have a universal set of quantum gates. Otherwise, you would just explore a corner of the Hilbert space, which doesn't lead you to the true solution, the optimal solution. And you want to have qubit-specific, single qubit measurement capability, which is, I think it's quite straightforward itself. So keep in mind those 5 criteria. Those are widely used. And next, I'm going to talk about quantum hardware. So I think I'm running a bit slow on this. Let me move a little bit fast. So these are the 2 most widely used or mostly popular architectures in the industry. On the left, you have superconducting qubits, which is a quantum version of LC circuit inside what's called a dilution fridge, which can cool down the quantum chip into million Kelvin temperature. So it's really, really low temperature. The superconducting chip, the 2-level is introduced by you replacing the LC circuit, the conductor to a Josephson junction, and introducing non-harmonicity to the system, so that you can go from a harmonic oscillator to an anharmonic oscillator. And you use the ground state as 0 and first excited as 1 state. And here I also give a review paper on this architecture. On the right-hand side, we also offer, I also give a very nice review. This is a very nice review paper. So for ion traps, those ions, people usually don't have a lot of choice. We usually want to have really not a lot of electrons on the outer shell. So you have limited choices on the periodic table. Instead, people working a lot on the chip design, on the trap design, how to trap those ions. So this is what you see from fabricated from Sandia National Labs. And I think they have been working decades on those and leading to this. So this is nowadays a very widely used design, I think. And for the operations, unlike to the superconducting qubits, you're directly having microwave pulses sending to them. We need a lot of laser pulses to operate ion traps, which is one of the disadvantage of this architecture. So this is kind of the market map, and we can look at how many people are working on, and there's many people working on superconducting design, and less people working on ion traps. And there has been other platforms I didn't introduce, but those photonics and neutral atoms are also promising, and they're gradually catching up. What's the other two right now? And in order to benchmark a quantum computer, people have different platforms. What you want is we should have a cross-platform benchmark to tell you the performance, the quality of a quantum computer, regardless of your physical realization. So here I would just briefly introduce the IBM's definition of the three core metrics they use. The first, apparently, it's the number of qubits. If you want to make a quantum computer useful to actually run the Schwartz algorithms, you probably need 1 million qubit. That's what people are expecting. And so that's the scale number of qubits. And the second, it's the quantum volume. It's talking about the quality of the quantum circuit implemented on the hardware. So for that, you have, you're running certain circuits, but you have to pass certain error threshold. Once you pass that, you get a quantum value. If you don't, you don't get results back. So quantum value, it's basically telling you, how well we can run circuits on hardware, and people have been keep pushing upwards for this metrics. And there's a new metric recently proposed, I think it was this year. It's called CLOPS, circuit layer up per second. So it's talking about how fast you can run quantum operations on this hardware. And next, I'm going to make a comparison between different platforms, mostly on superconductors and ion traps. As we have been talking about, ion traps, the very nice thing about it is those are made all the same ions, all the same atoms. The superconducting qubits, they have fab quality differences. Each of them have different frequencies, and fabrication qualities have different lifetimes. This is not the case for ion traps. Ion traps are all the same, and it's known for high gate fidelity, which means less error in the quantum operation. But the cost is, it usually involves a lot of laser, and the gate operation is very long. So that for now, it can only run some shallow circuit, not a very long circuit. And it's also nice, and since the interaction between those ions, a Coulomb interaction, they have all-to-all connection, unlike the superconductors. So for the superconducting qubits, they're usually only connect to adjacent qubits. That's called nearest neighboring connectivity. The nice thing about it is it has very high gate operation, but lower gate fidelity. Also, I think measurement fidelity is also lower than ion traps. And to further, I think most people here coming to the lecture, at least known superconducting qubits and interested on this. I would like to emphasize one more connectivity problem. So for example, I'm having a quantum circuit, 4-qubit circuit, and I'm trying to run this, mapping this, and run this into the IBM Q hardware on the bottom. And the lines are representing the connectivity, whether two qubits are connected, and each dot, that's the physical qubit number. So let's do a very naive mapping to 6, 7, 4, and 1. Well, since on the software level, first and third qubit are not connected, we want to do a CNOT gate on that, but on hardware, they're not directly connected, which means we will not be able to directly run a CNOT gate on them. So the solution is we usually insert in swap gates into the circuit, and by transporting the quantum state of qubit 4 to 7, and we do the CNOT there, and then we swap it back. So this is known as the qubit mapping problem, and apparently this is not, one can optimize with pencil and the papers. So there has been proposed many algorithms. I think in later, Professor Wu Li will give a talk, and he has done very famous work on this topic. So that's the connectivity I want to bring. So consider now I'm going to talk about the accessibility of those quantum hardwares. It would be, because it's important if we have direct access to those hardware. Researchers can do a pulse level research. It'd be very good. So for IBM-Q, they're very nice. So they have opened a lot of 5-qubit and 7-qubit quantum hardware to the public. You don't need to pay anything. And there's one IBM-Q Jakarta. It has pulse level access. If you're working on compiling pulse level stuff, this will be your best friends probably in some time. Also, it has certain paid plans to go up to 127 qubits, maybe. This is what they have on the website. And the other known cloud platform is Amazon Braket. It has many other manufacturers which they don't do a cloud environment themselves. They just authorize their hardware to give you the access through Amazon Braket. And the price, nothing is free. Okay, all here it's not free, and you have to pay for according to your measurement shot number and how many tasks you want to run it. So this is the price. I was so as you see, there are many public accessible quantum hardwares, which is very promising. And next, I want to give a sense of scaling up. This is from IBM Quantum's roadmap this year. So they have been planning to go up to a 4,000 qubits hardware by 2025. So the three technology would make it. Is first, you want to do classical parallelization. So by using a single classical computer, you can parallelly control different QPUs, and that's kind of maximizing the using time. You don't have to wait your control on the first, then you control the third, control the second. You can do this classical parallelization, which I think it's definitely doable. And the second technique they're proposing is chip-to-chip connection. So this is kind of like what I would say has already been realized in ion traps. So in ion traps, the company IonQ, they already can cut a very long ion chain into two separate ion chains, separate them and bring them back. So this is similar to that. And the third will be quantum parallelization, which means you have 3 quantum chips. They're sitting in their own cryogenic stack, in their own dilution fridge, and they will be connected with a physical cable, and people would expect this gives a relatively low fidelity, but it's one way to scaling up. It's called quantum parallelization. I think ion trap people are doing similar things. They're putting ion chains, relatively short ion chains in each vacuum chamber, and they try to connect those chambers with vacuum chamber, optical fibers. And this is still on their way, very new. And I think that's it for hardware. And next, I'm going to talk about algorithms. So this is, this is the part I actually very familiar with. So, there has been quantum algorithms like Grover and Schro's algorithm. Those are kind of the classic quantum algorithms. But the problem is nowadays we don't have enough qubits, and we don't have error correction to run a meaningful task. I think for Schro's algorithm, people only factored 15 equal to 3 times 5 so far. I think that's it. Probably they're a bigger one, but not really fantastic. Really not large integer. And so when people talking about near-term algorithms, they're probably working on some variational algorithms. A variational algorithm, the pipeline, I put that on the right. So the key idea is you use a parameterized quantum circuit I have introduced before, and you use a classical computer to optimize the parameters inside those quantum circuits, and you either to a certain direction, but this direction it's different by task, and it's guided by something called a cost function to quantify how well you're doing on this job, on this specific task. For example, if you're doing a classification in machine learning, you can set the cost function as the distance between the label, the actual label on the test point, and the predicted label on the test point, whether it's a dog or cat, something like that. So you will, once you've done the measurement, you need to do some post-processing, data post-processing, to calculate this cost function. And the key idea is, you have this hybrid loop. You have a QPU and a CPU. The QPU is doing the quantum job. It's doing quantum operation, exploring the Hilbert space, exploring a larger space, a larger solution space. But the classical computer, it's also helping it to do the search by tuning those parameters. This is the idea. And on the left-hand side, it's kind of the application spectrum. So I think in the past maybe 5 years, there are 2 very hot topics in near-term algorithms, which is finding the ground states of quantum chemistry, condensed matter systems, and the other is doing combinatorial optimization. Nowadays, I see a tendency that people are moving more to variational quantum algorithms and machine learning, and they do something called quantum machine learning. This is a new rising field, which I'm going to talk in the next slides. Yeah. Here, I just want to give an example about what variational algorithm looks like. So VQE it's a very famous variational algorithms. It adopts the variational principle from quantum mechanics to estimate the ground state energy of molecules. So you would building a molecule as a discretized Hamiltonian, Qubit Hamiltonian, and express them all in Pauli matrices and linear combination of Pauli matrices. And then you will prepare some trial state. Depends on if you're borrowing knowledge from chemistry. If you just know nothing about chemistry, just initialize to 0, 0 tensor 0, 0 tensor 0, or 0 states. And then you measure the expectation value. Okay. And then you can calculate, based on this, you can further calculate some gradient and do a gradient descent to minimize this expectation value will directly be your cost function. And you're minimizing this by classically tuning the parameters in your circuit. And the goal is you want to find the ground state energy, which is the minimum eigenvalue of this Hamiltonian matrix. On the right-hand side, it's in experiment results. People have done that experiments on this molecule. And the ultimate goal is to reach chemical accuracy, which I think on this experiment, it's not well enough because they don't have error mitigations at that age, I think. The next is quantum machine learning. So the idea of quantum machine learning is you borrow some classical machine learning tasks and using this variational quantum algorithms, parameterized quantum circuit to replace the neural network and see if this gives you a better, less parameters, better performance compared to classical machine learning approaches. So the big areas including classification, generated model, which you're feeding real people pictures, but somehow you could generate fake pictures, which are not people, but from human perspective, you will not be able to see the difference. And other things, including natural language processing. So this is a rising area. A lot of people used to do machine learning, jump into the field and try to make a quantum version of things. And I think this is very interesting. And there are also many challenges in this area. So in the classical machine learning, there is a known problem as a gradient vanishing, which means the gradient you use for the training is gradually shrinking, and eventually you have a 0 gradient on average, and you're not moving anywhere. You're stuck in some local minimum. Here, there's a quantum version of that called barren plateau. So this is a very, I think this is a very long explanation. It happens when you have a global cost function and you using a random quantum circuit, and as your problem size getting larger and larger, the gradient will be smaller and smaller. As you see on the right-hand side, this is a 4-qubit case for the algorithm. On the left, this is 24 qubits. And this is almost like a plateau, okay, a plateau on the top, and you have, it's like you're playing the golf. You're trying to shoot the ball, the golf ball to this very bottom to find the global minimum, but there's too much flat. You don't know, the ball doesn't know where to go, and it's making the training very hard. Also, apparently there are noise issues. So this is a optimization landscape for some variational quantum algorithms. On the left-hand side, it's not corrupted by noise. On the right-hand side, it's a noisy simulation. I think I put a coherent noise, which means when you do a theta rotation on the Bloch sphere, you plus a tiny arrow, epsilon, This is the coherent arrow Professor Ding has been talking about last week. And I also put some other decoherence, like the polarized noise, depolarizing noise. And what's happening is it's making the landscape very noisy, and also it also shrinks the minimum value. So the landscape can be corrupted by hardware noise. And another challenge, it's the ANSA's design, because most of the time the searching space is really large. You don't know what could be the optimal circuit structure to use. This is still an open question. People have been working on doing automated design on this, and try to bring some domain knowledge to build the circuit, or they just use hardware efficient ansatz, which means this is hardware friendly, but not really problem efficient. This is a problem people should aware. And next, I'm going to, I think I'm running out of time, but maybe I can quickly look at the quantum stack. So this is for high performance computing stack, and this is what people are making comparison with quantum. So here brings the quantum stack. There are many levels of, let me quickly go through this. So suppose you're having an application, you want to find a ground state energy of a very complicated molecule. This could help you protect chemical reaction speed. And the algorithm you use will be VQE, Variational Quantum Algorithm Solver we mentioned before. And you're running this framework circuit model. Maybe it's people are usually familiar with QuCS language. We can run it on QuCS. And then the architecture level, you're gonna have many things like error mitigation. You're compiling, you're doing the gate scheduling. You need to compile your circuit into some native gate. Each hardware has its own native gates. And then in the control logic level, you would sending that into, well, you will finish the compiling and transpiling and convert everything into physical signals. And in the control panel, those physical wires sending the signal to the quantum chip, to the quantum hardware. So this is a lot of things that are actually happening in between, and that means, so I will skip this slide. This is a kind of recap, a connection from last week's lecture. And I have, assigned, Professor Ding mentioned a lot of survivor kits, and they're mostly in the intermediate level, in the framework, architecture, and the control level. And I think something we didn't cover last week was a different area in the, I think we can mainly divide this level into three research topics. The first is optimal control, how you compile the pulse, transpile to the pulse. The second is error mitigation, how you deal with noise. The third, it's resource reduction, which was not mentioned last week. So this means resource reduction means, for example, you want to use less quantum measurements to recover the same quantum state, and this is what classical shuttle does. Usually you just, but the cost transfer to more classical data processing. You can do less quantum measurements. So we think that's a reduction of quantum measurement results. For example, another example would be QuCS. This is paper working on, suppose you have a very large quantum circuit, but you can cut the circuit and run it into two small quantum devices. And so that you reduce certain quantum resources, and simultaneous measurement for VQE. I will skip that detail, but that's something when you do a measurement, you're also measuring, when you measure certain polystring, you can do certain data processing later to get the results for other polystrings. You can combine those polystrings into different groups and measuring them simultaneously. It's also a resource reduction. This is something I want to point out. So where are we going? Okay. So at least to me, I think nowadays, recent years, there's a clear tendency people want to start with NISQ devices and demonstrating a certain level of error correction, mostly on superconducting qubits. And now people are gradually bringing more new error correction codes, more suitable for ion traps. And it's great, very happy to see many computer scientists and engineers join the game and just keep improving the quantum stack. It's very exciting to see that. On the very top application level, we're still looking for some killer apps to demonstrating a useful quantum advantage could be used for industry problems. We don't know when will we at that stage, but it would be very exciting to see those. So the long-term version is, we have been talking about quantum hardware algorithms and stack. Let's think about future. Okay, so I would say probably you will not see quantum computers even in 20 years, 30 years, 50 years as a personal device. It will be more likely to sit around some other supercomputers and form a hybrid quantum center. And we will, in that time, we would just do the same thing, access them through cloud environments, which is similar to how we use supercomputers nowadays. So this is kind of the vision I think I have. Maybe other people have other ideas, and that's also great. And resources I can quickly go through. This is just some. If you're not familiar with the field, this is two very good platform for you to get started. So SciRate, it's a more selective archive, so people on there can, they think this paper is very good, it's very hot. They just they will cite it, and the highest the side, you kind of see what the community is caring about, what the research community is caring about. So this is a more selective, more to quantum computing area. And Twitter, it's a very unique social media platform, actually. We have really a lot of research people on this. They post their opinions and advertise their work. I think this is a good way to interact with the community. And apparently we have the market map. This is if you want to know more about industry, take a look, find out what interests you. And internships, I want to mention there are many industry internships. If you're doing a PhD, if you're doing undergrad, there's so many opportunities nowadays. But if you think you're going to join the industry after your graduation, you can start with an internship, and I think this will be great. So this is from IBM, IBM, Google AI, and Zapata Computing and IonQ. But there are more companies. In summer schools, just for those people getting to quantum computing, QuCS organize a summer school every summer, usually in the middle of July. It's more cost focused on some area. They have been talking about quantum basics, quantum machine learning, and this year they're going to talk about quantum simulations. The other summer school is from Los Alamos. that more research focused, you're gonna have intense research story with great researchers there. I think the leader used to be Patrick Coyce, but yeah, I think they're yeah, those are they have done great work on barren plateaus and quantum convolution neural networks. So this is very good opportunities I want to bring to everyone. And you know, don't forget you're not alone doing QC, studying QC. Find a community around. So here I take a screenshot from Duke University, Stanford, Harvard, EPFL in Zurich. I'm not sure, but yeah, it's they all have their quantum computing association, quantum computing club, and for people interested, they can gather together to do reading clubs and you know, code-based projects, cool stuff. You know, find a community around you, and if not, you can build one. That's actually one of my suggestions. Don't learn everything yourself. Build a community around. Just like you coming to this lecture series, and I am participating. I think we're gradually going to build a community to learn and study QC together, which is great. And other things is, you know, these are also for beginners. QuCS textbook, it's very good results. It's because nowadays they're updating to newest version. I think you can directly run in code on your browser. So yeah, it's good, very good for code-based learning. Doing quantum computing, you know, you don't do it with paper and pencil. You want to do some real coding stuff. And you can check tutorials from other softwares like Petabyte Quantum I used to work on, and Pennyland. They do offer some good tutorials on certain topic, such as quantum classifiers or some certain variational quantum algorithms. Attend some quantum challenge or hackathons. Nowadays, there's so many quantum challenges and hackathons. You can, you know, if you want to test, you know, your knowledge on this, give it a try. And also, it's usually paid in some way. I think Xanadu, Pennyland organize QHack each year. IBM has quantum challenges probably each season, not each season, in spring and fall. And they have an open science prize every year. Yeah, those are opportunities. You know, you can collaborate with other people from your institute to tackle some quantum challenges. It's fun. And last suggestion, I think, implement your own QC software stack if possible. Nowadays, there are just many open source quantum softwares coming out. You know, it's okay to you know, use them as building as already built tool, but those can be part of your software stack. Okay. Keep in mind you should have your software stack, and this will make you unique in the job market and in research. You know, if you have two state-of-art technique, why not combine it, right? So this is my suggestions, and thank you everyone for staying here, for your attention. I can answer questions and you know, just talk for a while. Yeah. Yes, this.
I saw this hands up on the audience.
Okay.
So, Jinlei.
Hi, Jack. This is JC. So, you mentioned burn plan 2 in your slides. So I wonder if there is a standard way to detect the existence of variant plateau?
Oh, okay. Very good question. You're not asking for solutions. I think detection, from my experience, I usually run that. It's usually fine below 10 qubits from my experience. Even if you know this algorithm is having a global cost function, and you're using hardware efficient on that, or some more random close to unitary circuit. I think this is mostly you have to do some simulation to tell you. I don't think there is a systematic way to tell, okay, at 15 qubits, we're going to observe barren plateau. I don't think so, because barren plateau, the zero gradient, it's on average sense. It doesn't, because the results was sampling among 200, 500 qubits, sorry, 500 circuit. So there might be one circuit, it's okay. You still have not large gradient, but good gradient enough for you to keep optimizing. Yeah, that's my opinion on this. Does that? Yeah.
So are you saying that we can claim that we observe barren plateau once we see like zero gradients on some of the circuits?
Yeah, I think we do, from my experience, we do sampling the gradient and see if how it scales. Yeah, because usually you see an exponential decreasing.
Okay, thanks, and thanks for your inspiring speech.
Oh, yeah. Thank you. Yeah.
Okay, there is another hands up on the participant.
Yeah.
Xing Ding, please ask a question.
Hello. Thanks for your presentation. I would like to ask about Xanadu technology. So in their technology, I see that they use a QMOD instead of Qubit. So can you help me to distinguish the differences between QMOD and Qubit in their technology? Yeah.
Oh, okay. I think those are mostly photonic systems. You will see, if you look at this blue box and you see Xanadu's platform, you will see 216 Q modes. Yeah, those are not qubits. Those are not directly qubits. Let me see, what's the best way to introduce that? I think this might take, I'm not sure if I can explain that in few words, but maybe you can send me an email and we can talk later. Or I think Xanadu's document might have some explanation on it. Will be easier to understand.
Okay, so for example, I'm interested in combinatorial optimization. So
okay.
from my understanding that if I use, for example, ion cubed, the maximum number of variable should be 11. But for Xanadu, it should be about more than 200, right? If I'm not wrong.
So let me tell you what I have experienced. So I think for combinatorial optimization, for optimization problems, depends on the problem. Sometimes you can encode. So those problems, usually you can abstract those as a graph. Some problems you can use 1 qubit, to encode one node in the graph. But some problems like a traveling salesman problem, you cannot do that. You require more nodes. Yeah, so I think you're right. For IonQ, you have at most 11, and Xanadu Q modes, I'm not exactly sure, but I think D-Wave, as you see, they have some advantage of qubit numbers, and they can do optimization, very large scale optimization problems. Those might worth trying to run some algorithm on those. That's what I would suggest.
Yeah, thank you.
Okay, yeah. Any more?
Okay, I think we already run out of the time. So thank you so much for Zhixin to bring this really great talk. And I'll send this. Oh, yeah, I'll send this recording to our website. And I think next week, Jinglei Chen from University of Southern California will bring the talk with title Introduction to Variational Quantum Algorithms. So hope we can also see in the next week. Yeah, thank you, Zhixin.
Thank you.
Thank you so much.
Yeah, see you next week.